Welcome everybody. Welcome to one more telecom seminar, which is hosted by the Technology Innovation Institute. I'm Dr. Daniel da Costa, currently a principal researcher at TII. As you know, we are running a series of telecom seminars along the last months. And for today, we are pleased to welcome Dr. Jakob Hoydis, who is currently a principal scientist at NVIDIA. He will talk about one of his latest achievements, which is the Sionna. I think it's Sionna, the pronunciation is an Irish name. And Sionna is a GPU accelerated open source link level simulator for next generation communication systems. So Dr. Jakob is one of the maintainers and core developers of Sionna. And it's a great pleasure for us to have him here to expose some of further details and the principles about this new open source library. So before moving to the talk, let me introduce Dr. Jakob Hoydis by reading his biography. So as I mentioned, Jakob Hoydis is a principal researcher scientist at NVIDIA. He's working on the intersection of machine learning and wireless communications. And prior to this, he was the head of a research department at Nokia Bell Labs in France. And he was co-founder of the social network SPRAED. He obtained the diploma degree in electrical engineering from RWTH Aachen University in Germany, and the Ph.D. degree from Supéléc in France. And from 2019 and 2021, he was the chair of the IEEE COMSOC, an emerging technology initiative on machine learning, and as well as the editor of the IEEE Transaction Wireless Communications. And since 2019, he's the editor of IEEE JSAC Series on machine learning, communication, and networks. He is the recipient of many prizes. In 2019, he got the VTG IDE Johann-Philipp-Reis Prize, the IEEE SEE Glavieux Prize, the 2018 IEEE Marconi Prize Paper Award, the 2015 IEEE Leonard G Prize, the Best Paper Award in IEEE WCNC 2014, in 2013, the VDE ITG Förderpreis Award. In 2012, the Publication Prize of the Supéléc Foundation. He has also received the 2018 Nokia AI Innovation Award. And in 2019, the Nokia France Top Inventor Award. He is a co-author of the textbook, Massive MIMO Networks, Spectral Energy and Hardware Efficiency. So Jakob, thank you once again for accepting our invitation. It's a big pleasure I'm confident we will learn a lot from your presentation. And without further ado, the floor is yours.
Hey, yeah, thanks a lot for the introduction. You've said it all. Yeah, it's great to be here. Yeah, thanks a lot for inviting me and to speak about Sionna. So that's it's an open source library that we have released roughly 6 months ago. And I will speak first a little bit about this library, what it is, what you can do with this, and the motivation behind it. And then I would like to speak about 2 concrete examples of research that we have conducted using Sionna. And I will explain this to you. So, okay, good. So just to set the stage, while 5G is now a commercial reality, most of us researchers focus on disruptive technologies for 6G. And although it's still in the air what 6G will be, there's some consensus that it will need to enable the creation of digital twin worlds, as well as distributed machine learning applications at unprecedented scale. And let me now just mention some of the most prominent research topics that many of us are working on. So first, it is planned to explore communication in the sub-terahertz band, which will open the doors to orders of magnitude higher throughput. Then there are reconfigurable intelligent surfaces that will allow us to favorably control the radio environment and to ensure great coverage everywhere. But 6G is not only about providing great connectivity, but it will turn the network into a sensor, which has countless applications, for example, for autonomous vehicles, road safety, robotics, and logistics. It's further expected that machine learning and artificial intelligence more generally will play a defining role in 6G, which could potentially revolutionize the way we design and also standardize communication systems. Closely related to this are semantic and goal-oriented communications that will enable 6G to not only be a wireless bit pipe, but to provide an application with the data it needs in the most efficient way. And lastly, massive MIMO, which was introduced in 5G, will be further pushed to the limits by the concepts of either totally distributed, cell-free, or very dense holographic MIMO. And there are, of course, many other exciting topics such as UAVs, satellite communications, computer vision for wireless, federated learning, and many more. Now, the reason why I've mentioned all of these topics is because I firmly believe that our community does not only need new theories, but also new research tools to enable the breakthroughs that will define communications in the 6G era. And let me now explain why I believe that this is the case. So first of all, research on technologies such as reconfigurable intelligent surfaces, as well as multimodal and radar-based sensing for communication, requires a simulation of a specific environment with a spatially consistent correspondence between physical location, wireless channel impulse response, and possibly a visual input. And this can currently only be achieved by either costly measurement campaigns or by rendering and ray tracing. But there's currently no tool that allows you to do both. Machine learning and neural networks will become increasingly important for transceiver algorithm and even the interface design. And researchers would therefore benefit tremendously from a link level simulator with a native machine learning integration and automatic gradient computation. But there's also no tool available that has these features. And lastly, link level simulations of 6G systems require unprecedented modeling accuracy and scale. So while cell-free or very large aperture MIMO systems need the computation of a very large number of signal propagation paths, the realistic modeling of terahertz communication system requires complex channel models that account for nonlinear hardware impairments. Also, the full potential of machine learning enhanced algorithm will only be seen on very realistic simulations that account for detail that has been ignored for simulation complexity and mathematical tractability in the past. So I think that all of these requirements are new. And so we therefore believe that our community needs new tools to actually be able to simulate such system. And that's why we have developed Sionna. So Sionna is a GPU accelerated framework for next generation link level simulations. It's a tool that has been developed by researchers for researchers, and its main purpose is simply to make our daily work easier. And so it's kind of the tool that me and my colleagues, and I hope many others, wanted to have for a very long time. So Sionna is designed for rapid prototyping of complex communication system, which allows you to go as quickly as possible from a research idea to a first proof of concept. And for this reason, Sionna provides a wide range of state-of-the-art components that you can simply connect to build sophisticated end-to-end link layer simulations. Sionna has native support for machine learning, which means that you can very easily replace traditional processing blocks by neural networks or augment them with trainable weights. And since we need gradients to update the trainable weights in our systems, Sionna is also differentiable from end to end. So you can think about it as a differentiable link level simulator. Sionna has native GPU support, but also runs on a CPU. And you can scale your simulations by either distributing components of your systems on different GPUs, or by replicating the entire system on multiple identical GPU setups to increase the number of Monte Carlo trials that can be run in parallel. And for those of you who are used to write for loops for your simulations and then wait a couple of hours to get a bit error rate curve, I think this will be quite a game changer. But I think for most purposes, having a single modern GPU is more than efficient. So we have put a lot of effort into the API design, which is supposed to be very easy and intuitive to use. Everything's nicely documented with references to the corresponding technical reports, books, or papers. and the entire source code is available. It means that it's very easy to build your own components by extending existing ones. All of the available building blocks are carefully tested so that you can fully rely on them for performance benchmarking with your own algorithms. And we think that this is a huge time saver because you can focus on research rather than re-implementing things that your research is not about or might be outside your area of expertise. For example, for me, I'm not a channel coding person, but I'm super happy that I can just evaluate my algorithms with the state-of-the-art 5G channel code on top of whatever I've done by adding 2 lines of code. And this just makes my research more credible and impactful with essentially no additional work. And lastly, that's the best part, I think, Sionna is free to use, fully open source. Everything is on the GitHub repository that is maintained and further developed by NVIDIA. And we hope that this openness will lead to more reproducible research in our community and incite many people to contribute components and to make their Sionna-based research results available to others. And we start to see the first contributions. We release the next release, hopefully this week. I will contain a couple of community contributions. There's someone speaking, so either it's a question, otherwise I would ask you to mute your microphone. Okay, thanks. Yeah. So now I would like to show you some of the components that are available in Sionna right now. So we have a fairly advanced forward error correction module, which implements all of the 5G LDPC and polar encoders, including rate matching. Then there's support for Reed and Muller and convolutional codes. And we have multiple belief propagation decoder variants. We have successive cancellation and successive cancellation list decoders, also with CRC for polar codes. We have a Viterbi decoder. And then there's interleaving scrambling, as well as many useful other convenience functions that you might need to generate bit error rate curves or exit charts. The second module into which has gone a lot of work is channel simulation. And we have implemented the full family of 3GPP 38.901 channel models. These are the TDL, CDL, UMA, UMI, and RMA channel models. And we have also some much simpler channel models as AWGen and Rayleigh block fading. There's also a flat fading MIMO channel with arbitrary antenna correlations and so on. And you can either compute channel outputs through a full time convolution of the input signal with a possibly time-varying channel impulse response, or if you assume OFDM, you can simulate things directly in the frequency domain. And we felt that it's very important to have the channel simulator integrated into the link level simulator to avoid switching between different tools or generating large data sets of channel realizations. And again, this gives you the possibility to test your algorithms on realistic industry-grade channel models with a few lines of extra code. So I think in many papers, people use, for example, Rayleigh IID fading just because it's easy to simulate. But with Sionna, there's essentially no excuse for this anymore, because with a couple of lines of code, you can now evaluate it on a much more realistic channel model. So the third module covers everything related to multi-user MIMO. You can define arbitrary antenna arrays and antenna patterns, or use existing ones from 3GPP standards. We have implemented a couple of baselines, for example, zero forcing precoding for transmission, a linear MMSE equalizer for reception, and everything also works for large multi-thread setups. And these features should be a good starting point for the simulation of more advanced schemes. Lastly, Sionna has an OFDM module that allows you to define a very flexible 5G slot-like frame structure. And you can define arbitrary pilot patterns for any stream. And we have implemented a simple least squares channel estimator with nearest neighbor or linear interpolation. And more advanced schemes under development. So in the next release, we will get turbo codes and BCJR, the decoding algorithm. We get a community contribution on for a channel model for fiber optical communications. I think that's really interesting. And we will also add soon nonlinear MIMO detectors such as LMMSE, PIC, K-best, expectation propagation, and maybe a couple of others. Now I'd like to spend some time explaining key design principles of Sionna. And yeah, so most parts, I would say all parts, are written in Python using TensorFlow. And all individual components, such as detectors, channel models, MIMO detectors, and so on, they are all Keras layers. And this means that you can simply connect the desired layers in the same way as you would build a neural network. And for the same reason, it's very easy to mix traditional algorithms and neural network components. And the other advantage of this design decision is that TensorFlow can automatically compute gradients through the entire system from end to end. And so therefore, Sionna can be seen as a fully differentiable link level simulator. Another thing that's very important is that all algorithms are expressed as operations on high dimensional tensors. And this means sometimes you go up to 8 dimensions. And the first dimension is always the batch size. And then you could have, for example, second dimension, number of transmitters, number of receivers, antennas, the number of OFDM symbols, the FFT size, and so on. And the precise dimensions really depend on what the tensor is supposed to represent. But this means that there are essentially no for loops at all in the source code where you would iterate across any dimension of a tensor. And this leads to embarrassingly parallel workloads that can be very efficiently executed on GPUs. But if you have no GPU, everything will also run on a CPU, just a bit slower. Now, the batch size dimension comes from the field of deep learning, right, where you simulate batches of examples and you do stochastic gradient descent on these batches. But in Sionna, you can think of it as the number of simultaneously executed Monte Carlo trials. And the limiting factor for the batch size is generally the GPU memory, and you can easily scale to multi-GPU setups to increase this even more. So since we deal almost always with complex valued numbers in communications, we have decided that the TF complex 64 is the default data type. So it means that each complex dimension is represented as a 32-bit floating point number. So while this precision is enough for most use cases, there are some components that need higher precision. An example is, for example, this channel model for optical communications. And in such cases, you can also use TF complex 128. So I mean double precision for each dimension. Now Sionna supports both of TensorFlow's execution modes. So there's eager and graph execution. And so with eager mode, you get instantaneous results as if you were working, for example, with NumPy. And this is really great for experimentation. But once you've settled on a solution and want to run longer training or bit error rate curve simulations, you can switch to graph mode by adding a simply Python decorator around the function you want to accelerate. And this gives you generally a tremendous speed up, typically a factor of 10x. Then there's also an experimental TensorFlow feature called Accelerated Linear Algebra, or XLA, which provides additional speed ups. However, not all components currently support this, but I think the number is rampantly diminishing, so there's just maybe one or two that can't do it. And lastly, it's also possible to write your own custom TensorFlow operations in C++, SLA, or CUDA. And this might be beneficial for operations that are difficult to express with the existing TensorFlow operations. So for example, the check node function in min-sum decoding, or the convolution of a sequence with a time varying filter. They are difficult to express with the TensorFlow API. It could be more efficiently done maybe directly in CUDA, but the implementation of custom operations is a bit more involved, but can sometimes provide very significant speed up or memory footprint reductions. Okay, now I would like to walk you through a simple hello world example. But I just see that there are Q&A questions.
Yeah,
so
maybe
we can. Should we take them at the end, or I don't know how you want to handle?
Maybe for the end we can. Yeah, just
okay, good. Then I keep them for the end and go through it. But otherwise, have also two. There will be, when I switch kind of the topics in my talk, I think this will maybe also the right moment to look at them.
Yeah, it's up
before
to you.
We move to other. Okay, good. Then I finish the Sionna part and look then at the Q&A. Good. Okay. Great. Okay, then let's have a look at a simple hello world example. So the goal of this example is just to show you how with Sionna, get a first feeling of how it would work to do something with Sionna. So here we'll try to simulate the coded bit error rate of a 5G LDPC code over an AWGN channel, kind of the hello world example of link level simulations. So typically, you start by defining a batch size, which corresponds to the number of simultaneously simulated code word transmissions. Then you define the code parameters, N and K, the modulation order, and the signal to noise ratio for which you want to generate a bit error rate result. So the next thing you do is you instantiate the required Sionna components for this example and connect them in the desired order. So for those of you who have some experience with Keras, this is the functional API to set up a model. So in this example here, we use a 60 QAM constellation, which has 4 bits per symbol. And so we create a constellation object, and then we need a binary source that generate batches of random information bits. So you see here we say batch size times 500 information bits. These will then be encoded and mapped to the constellation symbols. And the symbols are then passed through an AWGN channel with the desired SNR. The channel outputs are fed into an a posteriori probability demapper to compute log likelihood ratios or LNRs, which are then used by the LDPC decoder to recover the information bits. And that's it. Now you could run this immediately and you get a result, average over 1024 things, but you could easily increase the batch size to 100,000, and I think depending on the GPU, you can also do 1 million in one shot, and you can simulate the bit error rate curve in a couple of seconds. Of course, you could iterate per SNR point and so on. So this is just first example of how it feels to work with Sionna. But now a very nice feature is that you can make some components trainable or replace them by neural networks. For example, in this example here, I've made the constellation symbol trainable by simply setting a flag trainable equals true. And I have replaced the demapper by a neural network that I've called a neural demapper. So I haven't defined, you can't see how this is defined here, but this is just a standard Keras model for a neural network with the right input and output dimensions that I've called a neural demapper. And now in order to train and optimize here in this example, the constellation and also this neural demapper, we need to compute gradients of a loss function with respect to all of the training parameters in the system. So here you could, for example, add the binary cross entropy between the information, between the input bits and the output bits. You wrap everything into a gradient tape, and then you can essentially compute the gradients through this gradient taps. So in this last line, you compute the gradients of your loss function with respect to all of the variables that are included into this gradient tape. And then you could apply your favorite gradient descent optimizer, such as Adam, do this for many iteration and optimize things. Yeah, so that's the first example. Now, how to get started? If you're interested in Sionna, want to use it in your research, so I think the best way to get started is really by having a look at our webpage. It contains installation instruction, a quick start guide. You have a fully searchable API documentation, which you see, by the way, here on the right-hand side of this figure. And then, depending on your research interest and needs, you might want to have a look at the tutorial Jupyter notebooks. So this is a very rapidly growing list of examples we have. It really should allow anybody to get quickly started. So for example, if you're interested in single carrier simulations, you can look at pulse shaping basics. If you're interested in MIMO detection, you have basic MIMO simulation examples. And there are more advanced examples for channel coding, how to set up, I would say, rather involved multi-user MIMO OFDM transmissions with channel estimation, equalization, coding, and everything. And then we have quite a few examples where we show how you can use machine learning in such link level simulations. For example, how to train an autoencoder communication system or implement a neural network that essentially does the entire processing of an OFDM frame. We got recently a new tutorial that shows how you can work with channel models from data set. And this one example here is specifically about the deep MIMO data set that I guess many of you are familiar with. So it's a ray tracing based data set containing millions of channel impulse responses. And you can actually load this into Sionna and then simulate communication, make link level simulations on top. And then there are many more. Then if you have any questions, so there's the GitHub forum where you can either raise issues or ask any type of questions. And typically we respond I don't know, within the hour or so, if it's not too complicated. If you want to have a more in-depth introduction to Sionna, at the GTC conference of NVIDIA, which will take place a couple of days from now, there's a so-called Deep Learning Institute training lab, lasts for 2 hours. So I think there might be still some spaces left. You can register and attend this training lab. And this is really hands-on coding with Sionna. We have a white paper, and recently I also spoke in the Wireless Futures podcast that's maintained and carried out by Emil Björnsson and Eric Larsen. So if you want to hear a bit more about a fireside chat about Sionna, please have a look at this one. Good. Now, as I've said a couple of times, I would like to explain how and under which conditions you can contribute to Sionna. So Sionna is released under the Apache 2.0 license. And then we've chosen for the great freedom at office and for people not to worry about patent infringements and litigations. Okay, so essentially that you can use Sionna for almost anything you want to do without worrying about it. Secondly, we welcome very much contributions from third parties, typically through pull requests. And then we process, so this looks roughly as follows. We create a fork of the Sionna GitHub repository. You write your code that you document using Python doc strings. This is important because we generate the API documentation from it. You add a few unit tests and then submit a pull request. And this creates kind of an environment for us to exchange with you and to do a code review, etc. What's very important is that all commits you do must be signed off with the so-called developer certificate of origin. But this sounds more complicated as it is. So it simply means you add the -s flag to the git commit command. And so this DCO essentially replaces a contributor license agreement and affirms that you have written the source code and that you're allowed to submit it to the project. So we will then review your request and decide whether it will be added to Sionna or not. But it might be generally a good idea to reach out to us prior to spending a lot of time preparing a pull request, simply to make sure that you're developing a component that is of interest to a broad audience. So another way to contribute is by filing bug reports or feature requests through GitHub issues. And for any type of question that you might have and that you do not find answered on the website or that you don't want to ask on the forum, you could also send an email to sionna@nvidia.com. And so there's another update which we will release, I hope this week, maybe next week. So on the website, there will be a section called Made with Sionna. And this is where we feature research that is based on the library. And so essentially, when you have a paper that is based on Sionna and you want to make your source code available that contains some new components, or that simply make your results reproducible, we invite you to send us an email with a link to the repository and also to the paper, and we will then list it on this website. So this gives also your work greater visibility and that others benefit from the new components that you have developed. And in the 2 examples that I present today, so these are 2 examples of papers that we have written using Sionna. We put them there, and all of this code is available for you to use. Now that's all what it is, but there's one very cool feature that we plan to release very soon, and that I also wanted to advertise today, and that's ray tracing. So as I've said at the beginning of this presentation, there are quite a few 6G research topics that requires the simulation of a specific radio environment in a physically consistent manner. And this simply cannot be done with stochastic channel models. And sometimes you also want to get the visual representation of a scene on top of the simulated radio propagation. So think about maybe robots moving around some unknown territory, and you want to do some radio-based, I don't know, localization or something like this. So with Sionna RTX, we will bring both of these capabilities, so ray tracing for wireless and also for rendering, into Sionna, and so that you can render a scene, get the channel impulse response, and use it immediately for link level simulations. And the best thing is that you can do all of this from within a Jupyter notebook, so without the need to install any other software and with just a few lines of code. So, and as the name says, Sionna RTX embraces the RTX architecture for hardware ray tracing. And it's also based on the material definition language, which is the industry standard for sharing physically based materials. And so ultimately, Sionna embraces compute, AI, and ray tracing cores of GPUs for lightning fast simulations of 6G systems. That's it. And now I would like to speak about two examples that we have made with Sionna. But it might be now a good time to take a break if there and look at the Q&A related to Sionna before we move on.
Yes, we have 2 questions.
Okay, yeah, maybe I read them. So which other community contributions regarding the fiber optic channel would be welcome? I don't have anything specific in mind right now. So the best thing would be to have a look at when the module for fiber optical simulation comes out, to have a look at what it already supports, and then see what components are missing and what you might want to add, what's missing. So I can't really tell. So what we ever see will be based on the Fourier split step transform. And there are, I think there's some specific model for a power amplifier that's used there. But I think then it would really be boiling down to you having a look at this and saying, okay, this is something that might be missing, and I would like to contribute, or I need this for my research, develop it anyway. Okay, and the same holds for all other modules. So if there's, for example, we don't have much for full duplex communications. There's nothing. We don't have anything for OTFS. If you're interested into other waveforms such as OFDM, these are components that might be missing. There might be other types of MIMO detectors that would be interesting, other type of channel estimators that could be. So it's really, there's no limit. So can be anything, but it shouldn't be something super specific that maybe nobody else apart from you is interested in. Then there's a second question, is Sionna including URLLC link model, short frame structure, and end-to-end delay model, and queuing and transmission delays? So concerning short frame structure, yes, you can make things as short as you want. So that shouldn't be a problem. Introducing transmission delays, there's right now no specific kind of layer for this, but it's generally super easy to add a kind of a time delay or random time delay before processing things. And for example, in the example that I present now, so this deep learning based synchronization for uplink narrowband IoT, this is an example where you have multiple users that transmit with random time delays, and it's all about estimating these time delays. Concerning queuing, there's currently nothing because we don't have any traffic model. So it's a pure link level simulator. So there's nothing, there's no scheduling or no traffic model for now. Okay, then there's a question about testbed regarding reconfigure intelligent surfaces. No, we don't have anything. So, but that's something that has quite high priority for us. But we believe that the most appropriate way to deal with it is integrating it in a ray tracer. But it's also community thought, because I think that there's no consensus right now about the proper ray tracing modeling for RS yet. So that's something where we also hope for community feedback. But it's definitely on our list. But right now you can't do it. Could you share with us your presentation? Yeah, I can share my slides. Can you please tell us what the abbreviation Sionna means? Yeah, it simply comes from, it has some link to Shannon. So there is it's the kind of an Irish goddess so it's a goddess in Irish mythology, and the name patron of the river Shannon in Ireland. And so you can make, if you want, you can make a connection to Shannon somehow, but might be far-fetched. Okay. Yeah, and again, so you get the slides and you have all of the links to access the things. But typically, if you type Sionna GitHub, you find all of the links yourself. Okay.
Yes, the presentation, just to inform the participants, the presentation will be available at the II YouTube channel. So at the most next week, we will provide the presentation recording there. And for these slides, we can get it from.
Yeah, I give you a PDF version, so no problem.
Okay, thanks.
Not confidential material. Okay, great.
Okay.
So then let's maybe move on to the first example.
Yes.
Okay. So yeah, so this is something where we looked at how we can use deep learning to do the synchronization of the PRACH, so the random access channel for the narrowband IoT uplink. Okay. So just for those of you who don't know what this is about, so typically before a user can actually connect to the base station, it needs to go to the random access channel. It sends a preamble to the base station, and it essentially selects one out of a set of available preambles, and then the base station needs to detect, okay, which preambles are there, and it needs to estimate a couple of parameters like the carrier frequency offset and the delay. And that's then so that's what happens in the random access structure. And so we look at can we implement these NPRACH detection using neural networks. So but let me walk you through it how it works, because I think it's quite interesting. So a preamble in this thing consists of a sequence of single tone frequency hopping. So you can see this here. I hope you can see my mouse cursor. So you send for some time a tone, a sign on one frequency of 0, then you move on to another frequency of 1, then to another frequency of 2 and of 3. And this is essentially a pseudo-random sequence of tones. And they are all, so there are many different such preambles. They are all orthogonal. And they are essentially fixed by an initial subcarrier. So a user selects a random subcarrier on which to start. And then the cell ID essentially defines where you're hopping to. In the standard, you can have up to 48 user equipments that can simultaneously access this random access channel. And ideally, every user uses a different preamble. There's no collision, but this cannot be guaranteed. Subcarrier spacing for this is 3.75 kilohertz. And what is called a symbol group is essentially 5 symbols plus a cyclic prefix. So this one thing, so this light yellow thing is a cyclic prefix, and then you have essentially these 5 symbols, and this is a symbol group, and then you hop to another frequency. Then you have one repetition that consists of 4 symbol groups. So here, for example, you would see 1 repetition on the slide. Now the base station typically sets this configuration according to the channel conditions. So you can choose a number of repetitions from 1 till 128. So if you would set it to 128, then these sequences are really long. And that might be useful if you have crazy cell ready. So if you have tens of kilometers, then you might need this very large number of repetitions. Also, the cyclic prefix duration depends on the delay spread, and also it depends on the number of subcarriers that are available. And multiple configurations can exist of this. Now, so here's how it would look like. So you see here we have 12 different users. We have 12 subcarriers, and each of them has a different orthogonal preamble sequence. Okay, so essentially one user is defined. We're going to look at the brown one. This is defined through this pattern, and then based on observing this pattern, one needs to synchronize. Okay, so let's have a look at what's actually happening in a channel and why this is a complicated problem. So this is here the signal that's transmitted by the case user for the IS symbol of the M symbol group, and it's essentially just a sign, so a complex exponential with a given frequency, and you have the transmit power beta k of this user. So this is what the user transmits. Now what's happening in the channel is the following. First of all, you have a propagation delay. So it's the time of arrival. That's one of the quantities you want to estimate. So this introduces a phase shift. Then you have a channel frequency offset, so between the oscillator of the UE and the oscillator of the base station. And this introduces these additional phase shifts. You have a channel attenuation. So typically we assume block fading. This is not for users that move at crazy speed. So for the time we processes, this typically doesn't change. And if there's more than one user active, which is typically the case, then you get the summation of all of these user signals together. And on top of this, you have some Gaussian noise. Now I'll just write this equation on the next slide. And what the base station does is essentially it observes this for a given amount of time, samples the analog receive waveform, removes the cyclic prefix, and does a discrete Fourier transform. And this gives you then this kind of this frame of all of these received preambles. Then it would select the resource elements of one user. So it would look at one of these sequences, extract them. And this looks like this equation here. You get a term related to the desired signal. So for example, you see one component here, because of carrier frequency offset, you get actually inter-carrier interference, and you get interference from other users. So this is all interference from other users because of the preambles due to CFO. And so the problem now is, given this received signal Y, you need to detect which users are active. So you want to detect all of the users such that AK is equal to 1. For each of the active users, you want to estimate the time of arrival. It's called DK. And for every active user, you want to estimate the carrier frequency offset. And so a couple of remarks. If there is no cyclic prefix, then there's no interference between the users. And if there is no delay, then things become even more complicated, more simple. Okay, but in practice, is of course not the case. Now, with respect to conventional methods, we benchmark, of course, against the state of the art. They don't use any machine learning or deep learning. And typically, a couple of assumptions are made to make this problem tractable. So typically, one assumes there is no interference between users due to CFO. That's a reasonable assumption if the CFO is low. Then it's assumed that the channel is flat fading. And I think that's also reasonable because the channel has really small bandwidth. So the subcarrier spacing is 3.75 kilohertz. So that's really narrow. So I think that's a fine assumption. And then one assumes that the channel is time invariant, meaning in reasonable static environments and under low mobility, this is the case. There are two baselines from the literature. So essentially there's one baseline with a follow-up of the other that we have implemented here. And some key assumption there is that they independently process the candidate preambles there are. And you need to, there's this one parameter, like a hyperparameter that you need to set for user detection. And this kind of controls the trade-off between false positive and false negatives in the user detection. And it estimates first the time of arrival and then the CFO. Now, what we have done here is we've come up with a neural network-based solution that does all of this in one go. And the way this works is as follows. So we observe the time domain sequence YT, will be sampled, cyclic prefix is removed, and we do a DFT. And this gives us a long vector essentially of so essentially gives us essentially a big matrix of complex values. And then we stack the real and imaginary part, and we end up with a tensor of essentially size number of subcarriers times number of symbols times 2. So where 2 is real and so the 2 dimension, the last one are the real and imaginary part of Y. And this looks like an image, right? Where you have, instead of 3 color channels, you have 2 color channels. And then this tensor is fed into a fully convolutional ResNet that transforms essentially this tensor of size n times 2 into a higher dimensional tensor of size n times d. So essentially, instead of 2 last dimensions, we now have d dimensions. But everything here is processed jointly together, right? We haven't done any user separation. Then we extract for every user the corresponding pilot, essentially the preamble. So you know for every pilot pattern that there is, you know which resource elements you need to extract. Just to bring it, to make it clear. So here you can see it. So you would typically, you extract all of the brown ones, all of the red ones, all of the yellow ones, one for each user. This gives essentially a vector for each of them. Okay, and so now you have this for all of the K users in parallel. And then, so now you can see that this has now become something much smaller. So this has come something essentially number of symbol groups times 5, because each symbol group has five symbols, and we have kept D. So this here much smaller. So you get, for every user, get a small tensor of this shape. And now based on this tensor, we want to detect, is the user active, what is the delay, and what is the CFO. And this is done by 3 neural networks with the identical architecture, but they don't share the weights. So the first one gives you essentially a probability vector. It's essentially a binary classifier telling you is the user active or not. The second one outputs a real number corresponding to the delay. And here this is multiplied by the cyclic prefix duration. And the last one gives you the CFO, where you also make an assumption about a maximum CFO that you could probably detect. Now, the way you need to, why is this approach better is because the first part, this left neural network, processes everything jointed together. And this is where you can compensate for intercarrier and intersymbol interference, if there's any. So if there's a block fading AWGN channel without CFO, you don't need this block at all, because there's nothing in between users you wanna exploit. But this really helps to, before you start treating every user one by one, this thing kind of makes sure that you mix things together, look at it in a higher dimensional space to allow you to reduce multi-user interference and CFO. And yeah, and then the last one, so these 3 neural networks, they are of course used across users. So for every user, it's the same neural network that's being used. And so this architecture seems to work extremely well. Yeah, so by the way, just in case you're wondering, so what is a ResNet? So you have these ResNet blocks where each block does first some normalization to make sure that things don't explode. Then we have an exponential linear unit, not a ReLU exponential linear unit. Then you have a 2D convolution, you normalize things, nonlinearity convolution. And then you always have these skip links or residual connections in between them, and you repeat this a couple of times. Now just to show you some results, there's a lot going on here on this slide. If you want to maybe get details on each of these figures, I invite you to have a look at the paper, at the repository. For example, if you focus on the false negative rate, so you can see that if there is no CFO at all of the kind of benchmarks or all of the results are roughly perform equally well. Ours is a couple, maybe still 1 or 2 dB better, but that's really not a game changer. But as soon as you introduce CFO, for example, at 10 parts per million, you really start to see actually, yeah, you start to see actually huge gains. And sorry, I mean even for no CFO, actually this is where we see the biggest gains. So you get 10 dB with respect to the baseline. It's just when the CFO is really high, then there's not much you can do. So then it becomes a really, really difficult problem, and then all of the approaches kind of fail. If you look at the time of arrival MSE, so this is where this neural network approach really shines. So it operates in a totally different region as the baseline, and something similar happens also for the CFO estimate. So it's really it operates in a region where you can't even reach with the baseline. But one needs to also keep in mind that all of these methods work well. So you go from 10 to the -8 to 10 to the -9. So I don't know what operational significance this chain would have. It just shows you that it works really well. But I think what's far more important is the time of arrival estimate and the kind of the detection performance. Yeah, so that's this one result I wanted to talk about. It was brief, but if you want to reproduce things, look at GitHub. It's all there based on Sionna. One of the things you can do with it. that contains, of course, many new components we developed for this work. So, for example, this whole narrowband IoT baselines, they are not a part of Sionna, but they are all implemented in the GitHub repo. Then the second kind of example I wanted to discuss is graph neural networks for channel decoding. So we recently looked into the question whether it's possible to learn linear block codes. And so what's a linear block code? So a linear block code is typically a code that is defined by a parity check matrix. For example, here you have a 3 times 7, that's the famous 3-7 Hamming code. The way you can think about this parity check matrix is that you have variable nodes and check nodes. So variable nodes correspond to essentially the coded bits. And now each column of A defines a parity check, meaning, if you look at these 3 coded bits, so you look at the first 3 bits of any code word, they must have even parity and so on. Now you can decode such linear block codes using belief propagation, which is a message passing algorithm, which typically works as follows. So you treat variable and check nodes. They define a graph, a directed graph, and a bipartite graph. So you have 2 types of nodes. I don't know why it's always jumping to the next slide. And what happens is that you start by giving every variable node a log likelihood ratio that comes out of the channel, typically from the DMapper. And then the variable nodes, they send their kind of these LLRs, they send them to the check nodes. So these are the messages that you send to the check nodes. And then the check nodes kind of process all of the incoming messages they get using these hyperbolic tangent applied to the messages, taking the product, and then the inverse of this again. And in the next step, all of the check nodes send their messages to the variable nodes. And then the variable nodes, for them, it's much simpler. They simply add all of the messages they get together and add to it the initial LLR they had. And then you iterate this a couple of times. And after some iterations, you read out, you take hard decisions on the log likelihood ratios at the variable nodes. And so we were wondering if you can actually learn to do this using graph neural networks. And so the way this works is as follows. So I just throw you the equations at it, but I walk you through it. So every node, when you have a GNN, it's again a graph, and every node, variable and check nodes, they have state vectors. So it's called HVI. So every variable node has a state vector HVI, and every check node has a state HUJ. And this is essentially, think about this as initially the LLRs. And then on top of this, edge nodes, edges, and all of the nodes, they can have trainable attributes that do not depend on the channel inputs. So these could be just numbers, for example, giving an edge a weight, for example, or giving a node a certain weight, but these are generally tensors. And then, so the thing this works now as follows is you seed your variable nodes with initial values to create this initial state vectors, HVI. And you initialize the check nodes, HUJ, they're all zeros. And now you compute the messages that the variable nodes send to the check nodes. And this is done with small neural networks, like we use MLPs with 2 hidden layers. Okay, so the first line here means the message variable node I sends to check node J. So what happens is, to compute this message, you take the state of the variable node I, the state of the kind of the recipient HUJ, and you concatenate them together with the trainable attribute of the edge. This is just one large vector that you feed into an MLP, and that outputs another vector with the messages. And here, so this is this function FM. This is a small MLP with FM outputs, and it's defined by these trainable parameters. So these are the weights of the neural networks, theta, MVU. These are the trainable networks of this. Now, if you want to compute messages that are sent from the check nodes to the variable nodes, that works in the same way. You concatenate the state vectors and the attribute of the edge, concatenates them together and feeds them into another neural network. And now in order to update, so what's happening in this algorithm is that all nodes always update their states. And this works to these node update functions. This is third and fourth line. And what's happening here is that you concatenate the state vector of the node that receives the message, HUJ. Then you concatenate this with the mean of all of the received messages. So in the classic BP operation here, you would take essentially the sum. Here you take the sum of all of these incoming vector messages that arrive and normalize it by the number. So it's the empirical mean. And you also concatenate it with the trainable attribute of this node. And then you send this into as input of another small MLP to compute the new node state. And here the last equation is just the equivalent for the check nodes. So, but it's the same. Concatenate your own state with the average of the incoming messages and your own attribute and feed it into an MLP. So this is here the algorithm, how this looks like. I just wanted to mention 2 points. So we typically get LLRs for every bit. So for every node, this is a scalar value. And we operate here with vectors. So what we do is we multiply, so this is line number 3, we multiply the scalar LLR by a vector W. Think about this as an LLR embedding. This might be a vector of size 8. Okay, and this is how you seed your initial values. And at the end, when you want to read out the LLRs to compute hard decisions, we do the inverse. So we take the state vector of a variable node and takes the scalar product with a vector Q. So that projects it back to a scalar. So it's the inverse operation of the first thing. So this is how we go from vector to from scalar to vector space. And then this is now everything is differentiable. You can transform to end. And so this GNN is defined by 4 small MLPs, independent of the size of the graph. So it's the 4 small MLPs. So it's a really low number of parameters. But on the downside, you need to think that you will execute each MLP many, many times. So essentially for every edge you have, you execute your MLP in an iteration twice. And so this can be in the tens of thousands. And this makes this actually not a low complexity algorithm, although the number of weights is really, really little. And now I wanted to show you some results. So for some reason, people in the machine learning for coding community, they always use this 63.45 BCH code as a benchmark. So we did the same here. So we trained our GNN for 8 iterations. So 1 iteration means variable nodes send update to check nodes send update to variable nodes. That's 1 iteration. Okay. We trained this for 8 iterations. And now you can see here performance results for like a classic textbook BP decoder with 20 iterations. Then you have the weighted BP algorithm where you use a classic BP algorithm, but every edge gets essentially a trainable weight. You can optimize this. And then there's the best known kind of machine learning based solution we know of in the literature is the ECC transformer that is in red here. And in green, it's the fully learned GNN approach for various numbers of iterations. So the nice thing is that this GNN, you can, although you have trained it only for 8 iterations, you can run it for an arbitrary number of iterations, for example, even for 10, and it still gets better. And already for 3 iterations, it outperforms BP. I think this is quite surprising that this works. In order, actually, we have noticed that the performance really depends on the hyperparameters. And by hyperparameters, I mean the structure of the MLPs you use. And so we did a very lengthy hyperparameter search using actually Bayesian optimization to figure out which are the best, and where we tried different activation functions, which number of iterations is the best to train on, what are the dimensions of the messages that you send, how many hidden units you should have in the MLP, how many layers you should have had, what aggregation function to use, and how to clip LLRs you compute. And so finally you see, so we find that hyperbolic tangent works best. It was nice to train on 8 iterations, having a message size of 20. So all of these messages you exchange, they're all 20-dimensional vectors. This works well. Having 2 hidden layers is sufficient. Yeah, mean aggregation is the thing to do. And this is how we trained it. So it's actually, if you try something else, and for example, you try an MLP with 1 hidden layer, you don't converge at all. Okay, then, but we wanted to do far more kind of exciting experiments. We wanted to see if actually we can scale this to much longer block lengths. And so, for example, one thing we did is we took a regular 3.6 LDPC code, it's code rate 1/2, and we trained this for 20, so essentially for 20 iterations. But the GNN is only trained once for a block length of 100. And then it takes the GNN that's trained for a block length of 100 and tried it for 500 and 1,000 bits, and it just works. And I think this is kind of a very cool result that this now scales. But the caveat is, of course, that this is for a regular LDPC code, meaning you know, every node gets either 3 or 6 incoming messages. So, but the practical LDPC codes, they are highly irregular, and you need to deal with this as well. So to look into this, we took now LDPC codes from the 5G standard. Trained the model for 10 decoding iterations on a code of 60 information bits, 140 output bits. And then you can play, essentially, you can change the code rate or the block lengths by changing the lifting factor in the LDPC code. You essentially keep this TRAME code structure, but are able to explore different code rates or block lengths. And it turns out that in both cases this works. So when we trained only on this one scenario, we could go to varying code rates with 280 bits block lengths, or we could actually change the lengths for the same kind of code rate. And I think that's also really nice. Yeah, that's the end of my talk. Just some final remarks. So I mentioned that the decoding, this is really nice. The decoding complexity is much higher than that of PP because you need to compute all of these messages through the MLPs. So the right network architecture is finding it is a challenge. So we have used a very costly architecture search. We didn't see any positive effects of having edge or node attributes. So we were expecting that it should have some benefits, but we couldn't kind of exploit it. And lastly, so the nice thing about this GNN approach is that it extends immediately to non-binary codes. For example, if you look at quantum communication, you could use it there, and also arbitrary channel models. And yeah, so that's it. I just finished with pip install Sionna if you're interested. Yeah, and now I would still have time for questions if there are any. Thanks.
Thank you. Thank you so much, Jakob, for your very nice presentation. So, any questions from the participants? I have one general question. Actually, Sionna, as you mentioned, is an open source liquid level simulation, right?
Yeah.
Look in the future, is there any plan to expand Sionna for system level simulations?
It's a good question. So what you can do right now is you can do really complex multi-cell, multi-user simulations, but it stays on the link level simulation side. So we don't, because to go to system level simulations, you would typically need some form of physical layer abstraction, and that would then be a totally different story. So for right now, we don't have plans to do it. But it would be nice. So we've thought about adding components, for example, for power control. Because otherwise, if you do multi-cell simulations and you don't have power control, then typically you get no great results. So that would be something. But we don't want to push this further to really do. We don't try to do 3GPP compliant system level simulations or something like this.
So is there an ambition to be used for 3GPP compliant?
It's designed to be a tool for research. And we want to keep the flexibility. So if we start to introduce, I mean, for example, what's really nice is to have the 5G compliant codes. Especially what I think is great is to have the rate matching there, meaning you know, whatever block lengths and rate you throw at it, it will work as long as you respect it. And so you don't need to, you know, you don't say, I only have this rate 1/3 code from the DVB standard, and I need, I don't know, 16,000 bits. You can just throw whatever you want at it, and the rate matching takes care of it. So I think that's something I find really convenient. And it's also, I mean, typically, you know, these codes are so well designed that you can easily gain sometimes, you know, you get half of a dB just because you use the right interleaver, something like this. And therefore, I think it's important to get these parts right. But for example, having the exact reference signal structure or the exact push uplink channel structure, whatever, I think there's no need for this for research. That would make things rather slow. So,
okay, yes.
But for example, the channel models are fully 3GPP compliant. You could use them out of the box on top of any other
yes, regarding the channel modeling, actually this is very important. You presented the channel model that Sionna incorporates in its first release, but looking again for the future, for example, terahertz model, do you have have an idea when it to be incorporated?
We don't have it clearly on our roadmap. So, but it would be something rather easy to do, because I mean, first of all, we didn't do it because there's no agreed upon model yet available for terahertz. There are a couple of I think good models proposed. For example, I think about NYU SIM, for example. I think they have something nice. I think there's also other groups, even I think in the Emirates somewhere. I saw channel models emerging. It would be very easy to edit, but we haven't done it because there's no agreed upon solution. But it will come. This hasn't the top priority for us. The ray tracing part is rather more important than adding more stochastic channel models.
When will be released the second release?
I mean, we release continuously, so it's you know, we are now at release at 10. So hopefully this or next week there will be 11. It happens every other month or so. We hope at the end of the year to have a stable version 1.0, and the ray tracing part will come when it's done. So hopefully soon, but I can't really speak about exact dates.
Okay, we have 2 questions from the attendees. Okay, the first question is, for the decode example from the simulation SNRs you use it seems only in BPSK is considered. In which case the distribution of LRs is constant. Did you try the non-binary constellations? For example, 16 km or no AWGN channels to verify the GN decoder can handle the distributions generated by these non-binary constellations?
So we have tried this. So in the lab we've done many. This is still ongoing research, by the way. So this was just our first shot at it. This works. So this works. It's just a question of so these trainings take long. Although the MLPs are small, this takes long to evaluate, but it typically works. And this is also, by the way, where we expect to see even higher gains. So we tried this also for MIMO detection to see if we can use it there. With so you can do this definitely. It's always just so the problem there is always, you know, if you think about practical system where you have rate adaptation, it needs to work for all code rates that there are and so on, you know, very rapidly. And right now the GNN doesn't. So you need to train it specifically, you know, or it works for some nice sets of parameters, but it's not like a universal decoder module that works all the time. And then that makes it, I think, challenging.
Okay. Another question is, the base station support the GPU high power consumption compared to FPGA? And is there Sionna support on massive MIMO?
Okay, I don't know why we're now speaking about the base station here. So Sionna is not running in a base station. So just, you know, there is NVIDIA has essentially a software-defined 5G base station. It's called Ariel. That runs fully on GPU and also CPUs. That is available, but I'm not involved in this, and I can't really speak about this here. Now, is there Sionna support for massive MIMO? I mean, yes, you can simulate any type of dimensions you want. So we have tried this. You can do very easily 64 users, 256 antennas if you wish. So yeah, definitely, that's what it was designed for, to be able to deal with this.
I think the same can apply for semantic communications, right?
Sure. I mean, for me, semantic communications is replace the binary inputs, throw images or videos or what other things you might have added. And that's a nice thing. You can just pre-process whatever inputs you have with neural networks and include it in the mix. So definitely, yeah.
Yes. Any other questions? Let me see. Another question is anonymous attending. Will there be channel estimation functions for dispersive channels in the future?
For dispersive channels,
yes.
If you think about, I mean, I guess the question relates to optical communications. I mean, otherwise you can think wireless is also doubly dispersive in some sense. So I mean, that's if you think about a OFDM channel, that's there. So, but I'm not sure what you mean exactly by the dispersive. But if you think about optical communications, there's one module there, but we don't have, I think, really good baselines for how you would process things for optical channels. So that's definitely an area where community contributions would be welcome.
Okay, let me see. No. Okay, my last question is about a comment actually for you further elaborate when you compare Sionna with their link level simulators. So please, what would be the main benefits? I mean, which differentiates Sionna from the other simulators? I mean, what would be the main game changer?
Yeah, I think for me, there are essentially two. The number one reason why we've done this is because we wanted to have a differentiable link level simulator. There's nothing else that gives you gradients. You can step propagate from any point to any other. That's why we wanted to have it. And also this integration of neural networks in the physical layer flow. And the second one is that it's fully open source. There's nothing comparable. Nothing else exists. And that's also essentially, it's a tool we developed when I joined NVIDIA. We didn't, and we started kind of the kicked off the 6G research activity. We didn't have any link level layer tool available. And then we said, okay, we need to develop one ourselves anyway. And then we said, okay, let's make an open project out of it and have others contribute and benefit from it. So
yeah, the Sionna support real time and I mean real world data sets. I mean, there is a function embedded.
Yeah, so you can, there's a specific functionality to import channel measurements as channel impulse responses and simulate over it, but it's not designed to do real-time experiments. So you could also think about connecting it to software-defined radios. You can do this, but in a batch mode where you say, okay, I record some traces of IQ samples, and then I essentially process them in a batch mode, but it's not designed for real-time streaming applications like new radio, something like this. So that's really not, it's not designed for this.
Okay. Okay, any questions from the attendees? Yeah, if not, maybe we are running out of time. And I would like to thank once again Dr. Jakob Hoydis for this very nice presentation seminar. So if you'd like to say some final words, please feel free.
I think my last slide says it all. Yeah, I hope you get something out of it. Yeah, don't hesitate to contact me or us through the channels if there's anything you would like to contribute. No, it's really about also getting feedback from others. Yeah.
Okay, so thank you everybody. So this presentation will be available at the TII YouTube channel very soon. Okay, And so keep an eye on this, and you can get the recording. And for the slides, I suppose that people can contact you.
And... Oh, no, don't contact me. So I think the best is I sent you a PDF version of it, and you distribute it. So please don't contact me individually for getting slides.
Yeah, otherwise you get many emails. Yes,
exactly. I have enough emails.
Okay, so thank you very much. Thank you once again, and see you in our next telecom seminar.
Have a great day.
Thank you.
Bye-bye.
Bye-bye.